In next few videos, the idea is to take some grammar and successfully remove some unwanted features from this grammar G. So that is what we will do in next few videos. And these unwanted features are this epsilon production and unit production and useless symbols. So I'll define all of them, and it's like, for example, in finite automata, if you start with NFA with epsilon transition, you can remove this epsilon transition to get a equivalent NFA without epsilon transition, and then you can remove the non-determinism from the NFA to get a equivalent DFA. So the language remains same, you get equivalent machine. So here again you are starting with some CFL because it is accepted by some G, and successively you are removing something from this G which is not wanted, and then you are you get an equivalent grammar, not exactly equivalent. You have to remove this epsilon, and this is required. So if your language contains something other than epsilon, then if you remove this epsilon, this will be non-empty, and for this part you can get something which doesn't have any of these unwanted features. So let us start with this useless symbol, okay, and you will see why they are not wanted. So yeah, so take this grammar. It has non-terminals SBC and terminals this small a small c, production at this, and is the start symbol. Now what is the language generated by this grammar? So you will see the language is just this A star. So a bunch of not A star, it is A plus, because there is no empty production. It is A plus. Okay. So you see that this language is generated by just this production rule. So you do not need even B here. So if you just had this S going to A and AS, so that will generate this language. Now why this B and C and this small c are useless here? That's because, see, when you are deriving anything in any grammar, so you have a start symbol, say S, and then from here you are going through some intermediate steps, and then finally you arrive at something. So this consists of entirely of terminals, right? So there is a string of terminals. It doesn't contain any non-terminal at the end. Now you use all the other variables in some intermediate step, right? So that means in the middle somewhere you have some, say, x, okay, and not just x, so you can arrive at something which contains x. So in general it will look like this alpha x beta, okay. So in the middle you use you hit upon some sentential form which contains this symbol x. So this can be a terminal, this can be a non-terminal, but it's a single symbol x, right? And this alpha and beta are strings over both terminals and non-terminals. If you remember the convention, the notational convention we talked about, and that's what we settled on. So yeah, so now that means it has two aspects, this x. first of all, you should be able to reach this x from this s, right? And secondly, this x must expand into some terminals, right? Because from here this alpha will expand into a bunch of terminals, beta will expand into a bunch of terminals, and also this x should expand into some bunch of terminals. So you take the concatenation of all these things, and that thing is w. So it has some part which belongs to alpha, some part which corresponds to this beta, and some middle part which corresponds to this x, right? So x should satisfy this two thing, that it should be reachable from s, and it should generate some string which is a part here, string over terminals. Now you see this capital B and capital C fail in that respect. So first of all, we define this term generating and reachable. So you take any symbol, it can be either a terminal or a non-terminal. So it is generating if and only if. So it's if because it's a definition. So it's a generating if you can derive some string over terminals. So this x is a string over terminals. So if you can derive some string over terminals from this symbol, okay. So you see that by this definition, all the symbols in terminal is generating. Why? Because this is star, so we are also allowing 0 step, right? So if you have any symbol, say a, so in 0 step it will derive itself. So by definition the entire T is part of this generating symbol, and that will in general not be the case for V. So some of them may not be generating, and you see that they won't take part in any of the derivation of strings over terminals. Okay, so if we are talking about L of G, if we are talking about this L of G, so that means we are talking about strings here, and these strings are strings over terminals, right? And when we are deriving those strings, this non-generating symbols will not take part in that derivation. And here you can see that this B, this is not generating. Why? Because if you try to derive something from B, okay, what can you, what production can you use? You can only have this production, so there is no other B production, right? So what is a production? Which has something in A in the left side. A B production is which has something in the, which has something B, which has B in the left side, right? So A production, B production, S production, you remember that definition. So the only B production we have here is this, right? And you can apply it indefinitely, but what will you get then? So you will get BB, then you can expand this B into 2 more B's, this into 2 more B's. So you will get a bunch of B's only. So from this B you will get only this B to the I, but you will never generate anything over terminals, right? So you will never generate some X over terminals. So that means this B is not generating, so it will not take part in any derivation. Now similarly, here you see that this C is generating, because as I said that all the terminals are generating. So C is generating. Also, if you see this capital C, this is also generating, because you see from here I can just generate C, which is terminal, right? So C is generating, but C is not reachable. Not reachable means you cannot get a C here starting from a S here. So the definition is some symbol is reachable if you can derive this alpha x beta from S, where this alpha and beta are some strings over both variables and non-terminals. So if you can do that, then we say that it's this x is reachable. And here we see that though C is generating this C and small c, they are not reachable, because you see from S, right? From S, what are the productions that you can use? So either you can use this AS, right? So consider a leftmost derivation. So in the leftmost derivation, what happens? You expand the leftmost variable always, right? So from S, you can derive say AS, then from here again, since you are doing leftmost derivation, so you will again, so you can keep on using this thing. So after some time you will get some a to the I S, and at some point of time you will have to use something else. So that something else can be just a itself. So you can end with some a to the I plus 1, or you can use this B. So this can either end in say a I plus 1, or from here you may have another path where you have AI and then a B. Okay, so and this B, we said that it can only derive this a bunch of B. So from here again, if you do a couple of steps, you will get something like a to the I and b to the j, right? So S can derive only this sort of sentential forms. Okay, so that means it from S you cannot get to this capital C or small c. So these are not reachable, right? So you see that this thing and this thing fail in two different ways, that this B is reachable but not generating, these things are generating but not reachable. You can have something else which is both not reachable and not generating. But anyway, if a symbol is not generating or not reachable, we say that it is useless. Why useless? Because it's not taking part in any derivation. It's not doing anything useful here. In deriving any string for that language. So it is quite obvious that if we remove these useless symbols from our grammar, and also you have to remove the associated productions, because if you remove B from here, you cannot have this production anymore. So you remove all those things, and then you are left with this grammar, right? So the only production here is production involving S and A. So this is what you are left with from this given thing, and you see that it generates the same language. So as I said, this is sufficient. So in general, so for any grammar in general, we define this generating, reachable and useless. So X is generating if you can generate, you can derive some string over terminals from X. X is reachable if you can derive some string containing X from S. That is alpha and beta strings involving both terminals and non-terminals. And X is useless if it is not generating or if it is not reachable. It can be both also. And we have this theorem that if you have some grammar, you consider its language. So you can have equivalent grammar, say G prime, by removing all the useless symbols. So we are removing all the useless symbols and also the associated productions, the productions which has some useless symbol. So then the language is the language doesn't change. So we have an equivalent grammar, and then this G prime does not have any useless symbol. Obviously, we removed all the useless symbols from G. So here we do not have any useless symbols. And to write a formal proof, you see that since we are removing some symbols from here and here, and we are removing the associated productions from here, so this and then we get this v prime, t prime, p prime. So this v prime, t prime, p prime are subsets of this v, t and p which we had for our original grammar. So obviously if you can generate something in this smaller grammar, that you can also generate here because it has more number of it has a superset of symbols and productions. So obviously this part is most obvious, that the language here is contained in this language. And on the other hand, to show this part, so suppose you can derive something in G. So these derivations are over G, right? So this S, we call that this is say alpha 1, and whatever we are deriving this W, so we call this alpha n, and this is over terminals in G. So if we can have such a derivation in G, so then we see that none of this alpha i's contain any useless symbol, because that's by the definition of useless symbol, right? So that means we can also have those derivations in G prime, right? Because G prime has all the useful symbols and all the productions involving useful symbols. So this productions and this symbols, this AIs are also part of this G prime. So we can also have that derivation in this G prime. So that means this is a subset of this, and together this and this tells that this is true. Now this part LG is not empty. Why is this required? So pause the video and try to figure out why this is required. Okay. Well, this is required because see, when is this empty? Now your grammar has to have some start symbol. That's by the definition of context free grammar. So it has to have some start symbol. So now if you have your start symbol and if your language is empty, that means you do not have anything here, right? So you cannot have this thing, because if you have this thing, then this WB in your this thing, but there is no W which is in this language, right? This is empty. So that means your S itself is non-generating. So this is non-generating. Right? So that means if you are removing all the useless symbols, you will have to remove S. But then without S, you cannot have this grammar. I mean, your grammar has to have some S, right? So if your grammar is say just this, say your grammar has this only S as a non-terminal, and the only production is say just S goes to S. So this is a valid grammar, but now if you try to remove all the useless symbol, what is your set of terminals? That becomes empty. So you do not have anything here to put, so it doesn't satisfy the definition of CFG. So that is why you cannot have this thing. So S is generating. So now this is pretty straightforward, that you take a grammar and you remove all the symbols that are not generating and not reachable in that grammar G, and you get that thing. So let us break this step down as follows. So this is something different. You will see that it's not exactly this previous thing that we first find all the non-reachable, non-generating thing and remove that from G in order to get this G prime. So here what we are doing is the following. So we are given this CFG G, okay. Now suppose we find all the non-reachable symbols in G, okay, all the non-reachable symbols in G, and then we remove that. So we obtain some G1, and we know that this G1 is equivalent to this G. Obviously we will assume that the languages are non-empty. I'm not writing that explicitly, but the language is not empty. So yeah, so this G1 is equivalent to G, okay, and then suppose we find all the non-generating symbol in G1, okay. So this is not same as finding all the non-generating symbol in G, okay. We will see in the example here. So we are finding all the non-generating symbol in G1, what we had here. So this G1 is already somewhat simpler than this G, and on this simpler grammar we are finding all the non-generating symbol and then removing that from G1, okay, and then we are obtaining G2. Now the question is, okay, so in this step also, I mean, it is guaranteed that this G2 will be equivalent to G1, so the language doesn't change. So the language here, and the language here, so the language doesn't change. But the question is, whatever we get here, so does this contain any useless symbol? So it at first glance it seems that it cannot contain. So we are first removing the non-reachable and then we are removing the non-generating. So why should it contain any useless symbol? But the subtle difference is that we are removing the non-generating symbols from G1, not from G, and you will see that it may create a problem. And we can do almost similar thing, but instead of removing the non-reachable first and then the non-generating, we first remove the non-generating, we get some equivalent grammar, and from this grammar, whatever we get, this simpler grammar, we are removing this non-reachable to get even simpler grammar, and then asking the same question, does this contain the useless symbol? So again, you may say that these two are same thing. I mean, doesn't matter which one we remove, but the thing is here, whatever you are removing at this step, you are removing it from this grammar that you generated as an intermediate step, not from the original Griffin grammar. So just take this example, okay. These are non-terminals. This A, B are terminals. S is start symbol, and the production is this. So this S can go to A or B, C, and this B can go to B, okay. So is the production clear? Now if we go via this route, so first we have to remove all the non-reachable symbols. So what are non-reachable things? So now you see that from S you can obviously get to A, from S you can get to B and C because this is a production, okay, and from S you can also get to the small b, because so from S you can go to BC, and then you can go to this small b C. So sorry, it's capital C. So by the definition of reachability, so by this definition of reachability, that from S you can get to some combination which contains this symbol. So you see that all the symbols, this B, C, A, B, so everything is reachable. So we cannot remove anything from here at this step. And then this is our G1. So G1 is equal to G, and you see the language is equivalent. And now we are removing all the non-generating symbols, okay. So which are the symbols which are not generating? See, B is generating. So what is generating? If you can generate some bunch of terminals from there, so B is obviously generating, it is generating this thing. And S is obviously generating because it is generating A. Now C is not generating because we do not even have any production for C. So C cannot generate any terminals. So C is non-generating. Fine, we remove just C. So if we remove C, then we have to remove the production. S goes to BC, but we still have to keep this S goes to A and B goes to B, right? We can only remove C from this step. So this is what the production is, right? So now what is the language here, you see? So from starting from S, you can only derive A. So the language is just this singleton set A, right? And you see that this B is not reachable here. So you cannot reach B from S. Because at this step, you could reach B from S because you had this production S going to BC, right? So that is why B was reachable at this step. But the moment you remove C, you removed this thing, and then B becomes not reachable. But now at this stage, you are only removing the non-generating. So B remains as a useless symbol in this G2. So you see that we have a problem. So do we have the same problem in this root? So now here we are removing all the non-generating. So non-generating are being removed here, and then reachables are non-reachables are being removed here. So here again, the non-generating thing is C, as I said. C cannot generate anything. So you remove C, and you are left with this thing. That the same thing here. And now you are removing the non-reachable, and here, as I said, this B is not reachable. So that means B will be removed from here, and you will be left with this. And this is obviously it only has S and A, and both are useful because again, the only derivation you can have here is just this thing. There is no other derivation, and there is no other string than this. So this is a grammar without useless symbol. Now the question is, we saw that this technique will not work. Now the question is, okay, this technique works for this given example, but will this work always, or can we find some example where this technique also doesn't work? And first of all, why do we need to consider this thing? We had a very clean thing here that you take the grammar and you just find all the not reachable and non-generating thing in G, no intermediate G1 or anything. So you find all those things and remove that in one go. So the point is, here in this step, when you are actually trying to find something, you are writing a program, or so finding these symbols will take time, and it will depend on how large this grammar is. That means the number of non-terminals here. And there are practical scenarios where this will contain some hundreds of non-terminals. So it takes time to find all this non-generating thing. Now, if you remove all this non-generating thing, you get something simpler, right? And then this step becomes simpler because you are removing non-reachables from this G1, which say contains, so this say contains 1000 non-terminals, this contains 500 non-terminals. So in this step, it is easier to find and remove the non-reachable from a grammar having 500 non-terminals than from a grammar which contains 1000 non-terminals. So from that perspective, this is beneficial. But even as a mathematical curiosity, if you do not care about all those algorithms and actual implementation and practical scenario, it's kind of interesting that does this breakup always work? And we will prove that it does work for all grammar. So this is what we have as a theorem. So we are given this grammar G, okay, so this G is given, okay, and then from here you are kind of going to this G1, okay, And how do you obtain this? By removing all the non-generating symbols. Okay, so from G to this, sorry, G1, not here. So this G1, so you are retaining all the generating symbols. That means, so generatings are retained. So okay, that's stupidity. Started. So you have some G, and from here you get to this G1, and at this step the generating symbols remain. Okay, and from G1 you are again going to this some G2. Okay, where you are removing all the non-reachable symbols from G1. So that means from G1 you are retaining all the reachable symbols. So reachable symbols remain. Okay, so this is your G1, this is your G2, this is the given G. Okay, so this removal is taking place from G, this removal is taking place from this G1. Okay, and as before, this language is not empty, and obviously, I mean, since we are only removing useless symbol, so we have that L of G is equal to L of G1 is equal to L of G2. So that is obvious. The only question is that do we have any useless symbol in G2? Okay, and we will prove that this G2 does not contain any useless symbol. And that's just going back and forth between this G1, G2. We have 3 grammars, so you have to be careful about which derivation we are talking about. So the derivation can be over G or G1 or G2. So just be careful while reading or following this proof. Okay, so now you take some symbol in this G2. Okay, so X is in this grammar, right? Now X survived this removal, right? So from G1 you removed some variables, and still this X remains. So what are the things that remain which are reachable, okay, in G1? So if X is reachable in G1, then only it remains in G2. So that means in G1 you can reach X from S, alpha, beta, some combination of terminals and non-terminals in G1. You see that this is happening in G1. So this is V1 and T1, right, corresponding to G1. Okay, now this means that it's this X was here, and the X was here. That means it survived this step also. So in here we removed all the non-generating things. So X must be generating in G, right? In G, X must be generating. That's why it survived, and it took, I mean, it is still in G1. So that means X is generating in G means what? And not just X. You see that all the symbols here, because all this this happens in G1, right? So that means all the symbols in alpha, this X, and all the symbols in beta, everything here, so that is in G1. So all that thing, this alpha, beta, X, so those are generating in G, right? So that means from here you can generate some terminal in G. So in here you can do this, and this W is in T. This is happening in G, so that is why this is in T, because all the symbols here are generating in G. So now what do we have? So this happens in G, and why does this happen? Because of this. See, all the productions, all the derivations here are subset of this, and all the derivation, all the variables here, all the productions here are subset of this. So if you can have some derivation here, that derivation is already here. If you can have some derivation here, that derivation is already here. So since you have this derivation in G1, you also have this derivation in G, and in G we said that this happens because here everything is generating in G. So we have this thing in G. Okay. Now we have to prove that this is a useful symbol in G2, not in G. So this kind of already proves that this is a useful symbol in G, and now we need to prove that this is a useful symbol in G2. Okay, because that's what we end up with. Okay, now if this is the case, then there is a chain of derivation from S leading to this W. Okay, call the intermediate strings alpha 1, alpha 2, alpha 3, blah 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 blah, up to alpha n. So this alpha 1 is S, and say alpha n is W. Okay, and in the middle, somewhere at some alpha I, you get this expression, this alpha x beta, right? This sits somewhere in the middle, and these are all single step derivation. Now you see that all these alpha i's, okay, so they are generating in G. Okay, not alpha i's, so generating symbol we said, so that means all the symbols in each of these alpha i's, right? You take any alpha I, any symbol occurring in this alpha I, so they are generating in G. Why? Because this is a derivation in G, and you see that from here you are ultimately leading to a terminal, right? So this is our terminal. So this W is our terminal, right? This is what we had. So that means any symbol here, if you take in anywhere in the middle, so that finally expands into some terminals, right? So that means all the symbols in this derivation, so they are generating all the symbols in this derivation, so they are generating in G, right? Because we are talking about G, right? So that means you see all of these symbols will survive this step, because at this step from G to G1 we are only removing the non-generating symbols. So generating symbol what we have, so that remains, right? So all those things will also be in G1, right? So that means we have the same derivation in G1 also. The same derivation, just this G I have replaced with G1 to denote that this derivation is also a derivation in G1, where all the alpha i's and W and S are same, right? Okay, from G1 now you see all the symbols in this alpha I, so they are reachable from S in G1. You see that now this is in G1, And in G1, what is happening? You take any symbol in any one of this some alpha t alpha or whatever, okay, in the middle, and you can reach that thing starting from S in G1, right? So everything here is reachable in, so all the symbols in this A, J, say alpha J's are reachable in G1. That's important. And from here to here, you see that if something is reachable, that remains in G2, right? So that means all the symbols in this derivation, all of them, they survive this removal process. So they are also in G2. So that means we have the same derivation in G2 also. So now we are talking about G2, right? Because they are also in, they are reachable in G2. All of these things are also in G2. So yeah, all the symbols here are in G2. So this corresponds to G2, right? V2 and T2. And now since we have this thing in G2, you see that this X is obviously useful in G2. So there is no useless symbol in G2, and this language of G2 is same as language of G. Okay. So this is the proof. Just to okay. Now now our example was very simple, but as I said, in a practical situation you can have CFGs involving thousands of non-terminals. Now, so here we discussed a systematic way of finding this generating symbols and finding the reachable symbols, so that we can remove all this non-generating symbols and non-reachable symbols. So again, we can use this two-step process. So yeah, we can use this two-step process. You start from here, you find all the generating symbols, you just retain those. Again, from here you find all the reachable symbols, you just retain those, and you get something simpler. So let us first discuss this process, how to find all the generating symbols. Now generating symbol means what? So X is generating, so X is generating if from X you have so from X you have something over terminals, and this is a multi-step process, right? It can take any number of steps. There's a star here. Okay. Now here we just parameterize this part. We say that so here we are considering all the symbols Vi. So Vi is a subset of V. V and T also, you can say that yeah. We are also considering this T. So this is the set of all symbols, such that you can generate something over terminals in less than or equal to I many steps. So this K is less than equal to I. So in less than or equal to I many steps, you can generate something over terminals. So those are in Vi. Okay. So you see that we are trying to find out all the generating things. So if so there must be some n such that this Vn contains all the generating symbols. So this is the set of all the generating symbols. Why? Because if this is generating, then there must be some n, some k, say there must be some integer, some k depending on x, right? Depending on x, such that these are something in terminal. And so this can be different from for different variables, but if you take all the variables and if you take the maximum of all the things that you have here, so that means in that many step from any variable you can generate something for terminals, if you can do it at all. So if it is generating at all, so then there is some n such that you can generate the terminals and within some n many steps. So now we will finally compute this Vn starting from V0. So the algorithm is that you start from this I equal to 0 and you compute this Vi plus 1 from Vi, and you compute unless you get this Vn. So now we need a recursive definition. So what is V0 then? So V0 means in 0 step you can derive something over terminals, and in 0 step means this thing itself has to be a terminal, right? So this V0 is actually the terminal itself. So x derives something over terminal in 0 step if x itself is terminal. So you see that V0 is just the set of terminals, right? And now you consider something in Vi plus 1. That means you can derive some terminals in I plus 1 or less steps, right? So if it is terminal, then it is in V0 obviously, it is in Vi plus 1. So either it is a terminal, or if it is not a terminal, so then in the derivation, in this derivation going from x to w using this something which is less than or equal to I plus 1. So the first thing should be a direct derivation which corresponds to a production, right? So this goes to this x1 up to xn, where this is a production, and then in some remaining step you go to some terminals. But go to terminal means then this x1 should so this x1 up to w1 up to wn, so these are over terminals, and then that means this x1 goes to w1, x2 goes to w2. Okay, so individually this xj goes to wj. So you can consider a leftmost derivation. Okay, so that from here you get first w1 and then x2 up to xn, then w1 w2, then x3 up to xn, this sort of thing. It's not that important, but the point is these derivations are kind of part of this derivation over this case step. So that means this kj are obviously less than or equal to k, which itself is less than or equal to I, because you have already have one step here and it is at most some I plus 1 step. So in this part this k can be at most I, so and this kj's are at most k. So that means all these xj's, so they are in Vi because of the definition, right? Because from here you are going to some w over these are terminals within how many steps? Within I many steps. Okay, so that means each of this thing are in Vi, and this is a production. This is a production, and each of this thing is in Vi. So if I call this thing, so if I call this thing alpha, okay, so then this is what we have for this Vi plus 1. So either it is a terminal, so you take the terminals union all the x's such that you have a production from x to alpha. Okay, x to alpha you have a production such that all the symbols here are in Vi. So this in Vi star means all the symbols here are in Vi, right? So yeah, this is precisely Vi plus 1. So in this way you can recursively compute this thing. You can write a program So start from 0 and compute vi from vi plus 1 from. Now when do you know that you have reached this vn which contains all the generating symbol? So you see by this definition, if you have this, okay, if you have this equal to this, so then again applying this process over this thing, so it's like applying the same thing over this thing. So again you get vi plus 1. So that means vi plus 1 is equal to vi plus 2, right? Because by definition you get vi plus 2, but this vi plus 1 was equal to vi. So if you apply this thing here, so then you actually get vi plus 1, which is this thing, and so it continues, right? So it doesn't grow anymore. So the index as per our definition is increasing, but the set remains same, right, because of this. So whatever this n is, however large this n is, so at some point of time it will hit this vn, so this will go to vn, but that vn you know is this vi, right? So that means as soon as you have this thing, that from v1 you try to discover some new generating symbols, you discover some, then again you try to discover some new generating symbol, you discover some. So at some point of time you see that at some step here you are not getting any new generating symbol, and once you have that, you know that you have discovered all the generating symbols, because if there is any generating symbol in this step, you are bound to discover some of them. So if you are not discovering anything here new, so that means you have actually reached this vn which contains all the generating symbols, and yeah, that is how you find this thing. And similarly, if you talk about finding the reachable symbols, again we can have this thing. So again, reachable means this s, this arrow start to alpha x beta, right? So in some steps it goes to some string which contains this x, so then we say that it's reachable. Now we parameterize again this so that the number of steps here is at most I, okay? So then we call that thing to be in vi, and again this alpha beta are symbols over the strings over both terminals and non-terminals. And here you see what is v0, so that means this happens in 0 step, and in 0 step s can only go to s, right? So this v0 is exactly the singleton set containing s. And then what is vi plus 1? So you see that this x appears in some derivation like this. So you take some derivation where this x just appeared, so in the last step, okay, we can change the order of the production so that the last step is where this x is first appearing in this entire derivation, okay? So you can think of this alpha 1, alpha 2 as alpha, this thing as beta, but yeah, you take some derivation where this x just appeared at the last step. So that means this must have appeared because we applied some production like this. So this x belonged to the right side of some production, and it has some variable in the left side. So that means in the previous step it was something like this, which contained this y, right? And then this y was expanded into this alpha 2 x beta 2, and this itself should be reachable from s using some steps. So from s you got this, and then after replacing this you got this. Now see, this entire process is at most of length I plus 1. So that means this number of steps k here, so this can be of at most this can at most be I, right? So is less than equal to I, right? So that means this y you can reach using I or less many steps. So that means this y is in vi. Okay, so y is in vi. So that means what is vi plus 1? So it is either in vi, obviously because of this definition. If it is reachable within I many steps, it is reachable within I plus 1 many steps. So you have all these vi's, or you can have this thing that okay, you can reach some y in I many steps, and from then this y, okay, so this should be x. There's a typo here, and this should be x. Please correct. So there's a typo. Okay, so from this y, then you can reach here. So this can also be the case. So you include all those things here. So you have this thing, and again, like the previous thing, you see that if you at some point of time see that okay, you are not getting any new symbols, so your I plus 1 is exactly equal to vi. So then from this point on, I mean, if you just apply this thing, you get the same thing as this v I plus 1. From again here you get the same thing. So the index is increasing, but anyway, and like previous we said that there must be some vn which contains all the reachable symbols, because if some symbol is reachable, it is reachable within some steps, and for each symbol, whatever that number of step is, you take the max of all that thing. So you take that as n, and then within this n many steps, any variable which is reachable at all can be reached using at most n many steps. So that means there is some n, and that n will be equal to vi if you ever hit this thing. So you start again with this I, you compute this from this, it's the same thing. Okay, and as soon as you hit that at some point of step you see that you didn't see any new symbol, so you know that you have already reached this thing. So this is how you find those things. And so you can take some more complex example. You can try to find examples. You can find questions in internet and other books, and it may have some grammar asking you to remove all the useless symbols, and you apply these algorithms and in this order to first remove all the non-generating, then remove all the non-reachable, and then you are left with a grammar which is equivalent but which has no useless symbol. So yeah, this thing, and using this